Now that we've taken a look at solving differential equations of higher order with constant coefficients, we're going to look at some applications that come from physics. We're going to look at the question, how do we model motion of a spring over time? And as we look at the differential equation that we're going to use to model this, let's draw a picture of what we're talking about. We have some spring. That's my picture of a spring. And it's going to be attached to some mass. That mass is going to be stretched on the spring. There's going to be some point in the middle, not exactly in the middle, but somewhere in there that we're going to call equilibrium, which is where that spring would be with the mass at rest. But we have stretched it down a distance of x, and we're going to release it with some initial velocity to see what happens to the spring over time. And if we ignore friction, this thing would actually bounce up and down for all eternity. And that's what we're going to start taking a look at, is where is that mass located at any point in time? Well, stealing a few things from physics, we know that the force on that spring is equal to mass times acceleration. But we also know that acceleration is the first derivative of the velocity and the second derivative of the position vector. In other words, we could rewrite the force of the spring as a mass times the second derivative of its position. We also have this relationship called Hooke's law, which states that the force on a spring is equal to the opposite of some spring constant times x, where that spring constant is unique to that spring. So we'll often have to figure out what the spring constant actually is. But what's nice about this is if both of these equations are equal to the force of the spring, the two equations must be equal to each other. So we can say that the mass times the second derivative is equal to the negative k times x. Or if I add the kx to both sides, we get a familiar looking differential equation that we know how to solve. I'm going to start solving by dividing by m all the way across. And then to make it a little easier to work with, we're going to introduce this new variable omega, where omega squared is equal to the constant divided by the mass. So we really have x prime prime plus omega squared times x equals 0. We know how to solve this. We need an auxiliary equation or characteristic equation. I don't want to use m, so let's use r squared plus omega squared is equal to 0. R squared is equal to negative omega squared, and r, when we take the square root of both sides, is plus or minus omega times I. Well, we know if we get these complex solutions, the solution is of the form x equals some constant times the cosine of omega t plus another constant times the sine of omega t. This equation then becomes the solution that can model the differential equation at a given point in time. And since it's always going to solve to the same equation, we'll just go ahead and use that equation, knowing that omega squared is the spring constant divided by the mass. With these two equations in mind, let's do an example. One note as we go into the example, it's really important we're careful with units. Our units must be in feet, if we're using the English system. And for the mass, in the English system, the mass is called the slugs. We're often used to thinking about mass as a weight, like pounds. But pounds is actually a force because it takes into account gravity. So to change to slugs, we can take the pounds and divide by the force of gravity, which is about 32. So for our example, let's say a mass weighing 2 pounds can stretch a string 6 inches. What we're going to do with this mass is take the mass and we're going to release it When we say we're releasing it, no time has passed at that point, so that's really saying time is equal to 0. 8 inches below equilibrium. With an upwards velocity of 4/3 of a foot per second. We're going to create an equation to model where this mass is located at any given point in time. But first, we have to fix the issue of units. We've got a couple units that can get us in trouble. 6 inches. We can't be in inches. We have to be in feet. So if we divide by 12, we get half of a foot. So instead of saying 6 inches, we're going to say 1/2 of a foot. We also have 8 inches. 8 inches, if we divide by 12, converts us to feet, 2/3 of a foot. So instead of saying 8 inches, we're going to say 2/3 of a foot. We also have the weight in pounds, which is actually a force. It's not a mass or slugs. So we have to calculate the number of slugs we have, which is the 2 pounds divided by the 32, which is the force of gravity, gives us 1/16 of a slug. All right, we take care of the units first. Now we're ready to start solving our equation. First thing we need to know is the constant for the spring, which comes from Hooke's law. Hooke's law said the force was equal to the negative constant times the displacement. Well, the force, that's a weight of 2 pounds, is equal to negative k times, we're going to stretch 1/2 of a foot downward, so negative. Negative times a negative is a positive. Watch your signs. The constant should always be positive. 2 times 2 is 4. The other piece of information we want is we need to know what omega is to plug it into our equation. We said omega squared was the constant divided by the mass. We just found the constant of integration is 4, and the mass is 1/16 slugs. Multiplying by the reciprocal, omega squared is 64, so omega must be 8. Put this all together, our equation from up above, we said x was equal to c1 cosine of omega t plus c2 sine of omega t. Plugging in what we know then, x is equal to c1 cosine of omega, which is 8t, plus c2 sine of omega, 8t. But we were also given some initial conditions. We were told when time is 0, the initial position is 2/3 of a foot below equilibrium, and our velocity is 4/3 of a foot. So when time is 0, we're 2/3 of a foot away from equilibrium. And if I look at the velocity, which is the first derivative, the velocity at time 0 is 4/3 feet per second. So let's find that derivative. That's negative 8 c1 sine of 8t plus 8 c2 sine of 8t. And if we plug in those values, first into the regular x, 0 2/3 gives us 2/3 equals c1, because the cosine of 0 is 1 and the sine of 0 is 0. And from the second equation, 4/3 equals 8c2. And if I divide by 8, we get 4 over 24, which reduces to 1/6, equals c2. So now we can take our equation and plug in the c1 and c2 to get our final equation that models the position of this mass over time. c1 is 2/3 cosine of 8t plus c2, which is 1/6 sine of 8t. And now we can figure out where that mass is at any given moment in time. What's interesting is if we look at this equation and we consider its graph. Turns out the graph of this is what we call harmonic motion. In other words, the graph is going to start up above with an initial velocity going up, and then it's going to start to bounce up and down around equilibrium, which is right in the middle there. You'll notice that looks like a sine or a cosine curve because it in fact is. If you remember from trig, we can take an expression cosine of omega t plus sine of omega t with coefficients and change it into a single sine or a single cosine. With that in mind, then, we can talk about the period of the motion, or how long it takes to make one revolution. And you remember from trig, period is 2 pi divided by the coefficient of our independent variable. In our case, omega. So we have 2 pi divided by 8, or pi over 4 seconds, for this mass to bounce all the way from one extreme to the other and back to where it began. Or we might be interested in the speed at which it's moving, which would be the frequency, or the hertz. The frequency is just the reciprocal of the period, omega divided by 2 pi. So in our case, 8 divided by 2 pi, or just 4 over pi cycles per second. Or the other thing we might be interested in to know about the graph is the extreme displacement. When you took trig, we called this the amplitude, or how high and low the graph goes from our equilibrium point. Now, using the Pythagorean theorem, it can be shown that the extreme displacement is going to be the square root of our constant squared, c1 squared plus c2 squared. So in our case, that's the square root of 2/3 squared plus 1/6 squared. And cleaning that up, we get 4/9 plus 1 over 36. If I want a common denominator, I'll multiply by 4, which gives me 16 plus 1 is square root of 17 over 36, or the square root of 17 over 6, which is a little bit more than 2/3. Now that we have an idea of what the graph's doing, let's see if we can have an online calculator actually find the graph for us. I use an online grapher known as Desmos at desmos.com, but there's a bunch of them out there. And if we type in our equation, you notice at time of 0, we're starting at a height of 2/3 with an initial velocity going up. Well, eventually the spring gets too tight, and so it pulls the mass back down past equilibrium until it reaches the other extreme to bounce back up, and it's bouncing all over the place. So if I wanted to model this graph, you could think about the wall up above, and then the spring is attached to the mass, which then bounces all the way down, stretched out to the end, and then it starts to bounce back up. And then this kind of shows us what the spring is looking like. Here it is at equilibrium, and it's just bouncing up and down over time in this perfect harmonic motion. What we're going to take a look at in future videos is what happens if our system has a dashpot or shock absorber attached to it. In that case, it's going to try and pull the graph back towards equilibrium. But before we get to solving those equations, first I want you to get good at identifying the key pieces and using these equations. So take a look at the homework, practice those, and good luck to you.